Okay, we use the weighted average. Okay, you can check later if you use known or if you use micro, you use macro, what is the difference from the result. And this is the testing result. 1 1 1 1, everything is good, so we can perform the other kind of performance using the hold up method. With the hold up method, we split into 60 20 20. Then you can see here the number of data for the training is 90 and the remaining is 60. And after we have the 60 for the X temporary, we can split again. Okay, we can split again the temporary data, which is using 0.5. Then the result will be 30 for validation and another 30 for testing. And after we have those, we can do the classification. In this case, the KNN with K equals to 3, N equals to 3. Yeah. And then we do the performance. So this hold out accuracy means we are doing the performance on the validation dataset. With the validation dataset, the result is good, 1 for all measures. And now we are doing with the testing dataset. With the testing dataset, the performance is this one. We have 0.96 and so on. Now, let's try with this grid search. So we want to know what is the best parameters in order to get the best result. Using the grid search CV, let's only split the data into train and test. And after that, you can check the range from 1 until 9. In this case, we are using the loop from the range value and we put into a list. And the parameter grid is a dictionary from the value k range into the parameter which is n neighbors. So we perform with the k and n. This is the k nearest neighbor, and then the parameter grid, which is from the parameter grid here. And the k fold that we use is split into 5. Shuffle is true. So it means the data will be randomly in different split for 5 times. And we use the accuracy, precision weighted, recall weighted, F1 weighted, Matthew correlation coefficient to get the best parameters. Next, we fitting the training and from the X and Y. Here you can see this one. If you click on this figure, you will see that the best parameter is 6. Okay. So you run from 1, 2, 3, 4, 5, 6, 7, 8, 9, and the best parameter is 6. You can perform, you can print what is the best parameter. In this case, the best parameter is 6. We can get the best estimator, which is 6, and we use the best estimator to predict the testing data. So after we do the prediction, again, we check performance, and the performance result is 1 for all. Okay. Now, we can do the classification with different models. We can do the model comparison and we can do the interpretation. For the other algorithm, sklearn, now let me just use the sklearn. We can perform several algorithms and do the comparison. We can select the best algorithm based on the performance metrics. So in this case, we choose the higher accuracy, we choose the higher precision, we choose the higher recall, we choose the higher F1, and we can choose also the higher MCC. So the category can be distinguished into this. In classification, we have the linear models. The linear models means we use the logistic regression. We can use the perceptron. We can use the linear discriminant analysis. For the tree-based model, we can use decision tree classifier. For the ensemble methods, we have random forest, gradient boosting, and AdaBoost. There's another category, SVM. We can use the spot vector classification, SVZ, and the linear SVZ, and so on. So we have the nearest neighbor, we have naive Bayes, and we have the neural network. This is the function name on Python. So if you want to run those algorithms, you can just call the function name. First, you need to call what are the models that you want to use. Let me just use the decision tree classifier, logistic regression, SVC, random forest, AdaBoost, and the metrics will be accuracy, precision, recall, F1, and MCC. Okay, you can take a look on the Google Colab. Now, I'm just showing you the performance measurement. So refer to the Google Colab for the performance metrics on the testing set and select the highest performers. Okay, if you look at this one, decision tree, logistic regression, SVM, it shows accuracy equals to 1, precision equals to 1, recall is equals to 1, F1 equals to 1, and MCC equals to 1. Okay, everything is 1. But the random forest is low, and the AdaBoost is also low. Why? Maybe you will ask why this is good algorithm, but why the performance low? This is also another good algorithm, but why the performance is low? This is because we use the default parameter. The algorithms, when you call the algorithms, you will have the default parameters. Let me get back to this Google Colab. So I will run the library for every algorithm. I do the split and test, and I will do this algorithm, decision tree classifier, logistic regression, SVG, random forest, AdaBoost. If you look at this algorithm, every algorithm has no parameter inside. It means if there is no parameter, they use the basic or the default value. If you put your mouse in the edge of this library, you can see the decision tree classifier. We use the criterion Gini. The splitter is best. Maximum depth is known. Minimum sample split is 2. Minimum sample lift is 1, and so on. So we use this basic parameter to run the decision tree. And let's say in the random forest, so you can see there are many parameters, and we use these basic parameters to run the random forest. One of the reasons with the bad performers might be these default parameters. Maybe we need to change some of the parameters to make it a better result. But now I will not discuss about the parameters. You can run by yourself. You can run with the grid CV to find the best parameters, and you can choose the best algorithm with the best parameters for your project. And we can do the performance. We can check. We put everything in a table like this one. Now, from this data, we can see the best is decision tree and logistic regression and SVM. The next thing, after we run this one, we need to interpret. We need to interpret. It means I need to explain why the result is good and what features are important when we perform this algorithm. Because the three are the best, so let's choose one. Okay. Decision tree. Decision tree is one of the most popular algorithms in the classification, and we can also look at the result by using tree. We can show the tree because the name is decision tree. We can show the tree, and we can just perform the plot tree to show the tree in the decision tree model. We call the sklearn.tree, import the plot tree, and the result from the classifier, which is the DT classifiers, and we call all the columns from the X and verify what is the class name. In this case, the class name is Setosa, Virginica, and Persicolor. We fill true in order to put the color into the tree. So this is the decision tree model. Okay. We are going to look at the details, how to interpret this decision tree model. We call the top, it is the root. We call root node. And the bottom is leaf node. The root is the most important feature for the discrimination or classification. If you look at this one, petal length, then it means petal length is the most important feature for classifying the flower, because it is on the top of this decision tree. And every node, this one, it will be followed with the condition true and false. The true means if the condition of this one is true. If you look at this one, the petal length, if it is too small for you, please refer to the PowerPoint. Here is the petal length is less than or equal to 2.45. So the petal length is less than or equal 2.45. If it is true, if the condition is true for the data, it goes to the left. If the condition is false, it goes to the right. Okay. Means if the petal length is less than 2.45, it goes to the left. If the petal length is higher than 2.5, it goes to the right. And we need to interpret the details. The leaf is the node that we cannot split further. Okay? The leaf is the node that we cannot split. In this case, we can still do splitting. We can split, we can split, we can split. That's why we call it this is decision. The decision tree means we can do the decision like a tree, like a tree, like a tree. Now, each of these box has a meaning. the first part, this is the root, okay, or maybe in some parts you can see also there are some white color box. Maybe in this sklearn they use white. In some other tools, maybe they have different color. So let me explain using this sklearn. The white color means there is no dominant class. The features can be split more. So if you look at this one, the leaf, what does it mean by leaf? The leaf node means the node that you cannot do more splitting. There is no splitting, no splitting. There is no split anymore from this one. It means you cannot do again. You cannot do again. So this is the last one. If you look at this one, because this is the last one or the leaf node, the color is dark. Color is dark. So the color, dark color on the orange, this is the class is dominant. Dominant means the class is many. In this case, setosa. Okay. Setosa is dominant in this part. Why it is dominant? You can check from this one. The Gini is 0 and the samples, there are 40 samples. So there are 40 data and the value is 40, 0, 0. It means from 40 data in this section, all 40 data belongs to class Setosa. Now let's see the second picture with the purple. So this is dark color. So the class is dominant. What is the class? The class is versicolor. And you can see the Gini is 0.2. Okay, this is not that high. If you compare with this one, 0.667. So the higher Gini value means the more important of that features. This Gini is low, then this feature is less important. And if you look at the data, we have 43 samples. Okay, we have 43 samples. And among the 43, the value is 0, 3, 38. So this list represents the first index is Setosa, the second index is the Virginica, and the third index is versicolor. Then how do we know this one? You go autoclear. At the first, you use the label encoder. What is label encoder? We change or we transform the categorical data into numeric. And from the code that we have, S is 0. The second one is the Virginica is index 1. And the last index is index 2 is the versicolor. Then it means that the index 0 is 0. This is Setosa. The index 1, this is the Virginica. And the index 2, this is versicolor. And the number of numerical data here is high. It means among 43, oh, maybe this is not 3, sorry, this is 5. Then the total should be the same with the sample. So the 43 data, 5 data belongs to Virginica and 38 data belongs to versicolor. So it is dominant on this number, then this versicolor is dominant. And in this case, yeah, there is almost no further splitting. Almost no further splitting means, yeah, we need to check if there is still possibility to split, yeah, because there are still 5 flowers in between 43, which is not in the versicolor, then we can split. If it is already 0, 0 like this one, if already 40, 0, and 0, so we cannot split further. If there are still some numbers, 5 and 38, we can split. If you look at this one, the number is dominant on the versicolor. There are 6 samples, and the value is 0, 2, and 4. Then Setosa is 0, Virginica is 2, and versicolor is 4. And the dominant is on the versicolor. The color is not that dark because, yeah, the portion of versicolor and Virginica is like 2 divided by 6, and the other is 2 divided by 4. Oh, sorry, 4 divided by 6. Okay. So 2 divided by 6 and 4 divided by 6. So the proportion is still quite high on this case. So just like 30%, 33%, and this is still 66%. Compared to this one, this is 5 divided 43 and 38 divided by 43. Of course, this is more dominant. That's why the color is dark, but this one is light. And also for the green color, the dark green color means the class is dominant on the Virginica. If you look at this one, 37. Among the 37 data, 36 data, okay, 0, 36, and 1. So among 37 data, 36 of them belongs to Virginica, and 1 of them belong to versicolor. And this is dominant on the Virginica. There is almost no further splitting. So we have only 1. It is almost, yeah, we cannot split anymore because it is only 1. And if it is a light color, green, then the class is not so dominant. In this case, we have 3 samples. We have 3 samples, and the value is 0, 2, and 1. 2. 2 belongs to Virginica. It means from 3 data, 2 of them are Virginica, and 1 of them is versicolor. Yeah, if there is still remaining like this one, sometimes we can still split. Sometimes it depends on the number of the data remaining in this section. Okay. Yeah, the figure in the Google Colab is not that clear, but let's look at one by one. The petal length, okay, it means this is the features that can split more because this is the root. Okay, this is the root. It means the most important feature is petal length, and the split point is 2.45. If the petal length is 2.45, true, then go to left. Else, go to the right node. Go to the right node. Gini. It is the metric to show the importance. High Gini value means high importance of the features. So the Gini value represent the importance of these features. Gini. 0. It means it is already done. We cannot split anymore. There is no features that can split. That's why it is 0. We have Gini 0.5. So the importance of this feature is quite high, which is 0.5 for this data. Samples. Samples in this node, there are how many data? In this case, this is the training data. Okay. The training data, before we have the data is 150 data. And among the 150, we split into 80-20. So 80-20, 80% from the data, which is 120, and 20% of the data, which is 30. So 120 is the training data, and this is the data. There are 120 data, and among 120 data, 40 belongs to the first, which is Setosa. 41 belongs to the second, which is Virginica. And the last one is 39. It is belong to the versicolor. So the value means the samples for each level. Okay. 40 is Setosa, 41 is Virginica, and 39 is the versicolor. The class means the dominance of the class in this set or in this node. Okay. If the highest value is Virginica, then it will show Virginica. If the highest value, this one, is here, then the class is Virginica. If the highest value is here, then this is Setosa. Okay. So this is how to interpret the decision tree. When the petal length is 2.45, less than 2.45, all the labels show Setosa here. When the petal length is less than or equal to 2.45, all the labels Setosa. So 40 of them are in the Setosa. The Gini is 0, means that there is no feature which is dominant. The value 4000 means the class is dominant on the first label, which is Setosa. On this side, the petal length again is selected for the next node. When the petal length is higher than 2.45 and the petal length is less than or equal to 4.75, then the dominant class label shows Virginica. The Gini index is 0.5, means that the petal length is the most important feature on this step. So on this node, this petal length is important. And there are 80 samples. Among those data, among the 80, 41 belongs to the Virginica and 39 belong to the versicolor. And the class, the dominant class is Virginica. This is the highest number among the other class. We can use Sharpe value to understand the features. If you still remember the Sharpe. Sharpe means Shapley additive explanation. It is an approach to explain the output of any machine learning model. And it assigns its features an importance value for a particular prediction. That is the Sharpe value. And the Sharpe value for a feature represents the average change in the model's output when the feature is included in the prediction compared to when it is excluded. Okay. With the classification, you can see later with this kind of figures. First, you need to install the SHAP. Check if you already have the SHAP or not. If your environment does not have it, then it will install it first. So you can use try and accept. Try to import the SHAP. If your environment does not have the SHAP, then you need to install the SHAP first and then import SHAP. Because last time when we learned about the regression, you already used this installation. I think you already have the SHAP in your computer. But if your computer, maybe if you change your computer to another laptop or to another desktop, you can use this one to manage the installation. Now, we will take a look later on the Google Colab. This is the result from the SHAP. We have the bar plot. Okay. So this is the result with the bar plot on the SHAP values. The bar plot means it is to understand the global importance of features in your model. We have the axis. Okay. This is the y-axis. The y-axis, this lists the feature names. So we have petal length, petal width, sepal width, sepal length. This is an order from the top to bottom. Okay. It is typically ordered from the most important features. So this is the most important features at the top to the least important at the bottom. So this is number 1, the most important. This is number 2, the most important. This is number 3, the most important features, and this is number 4, the most important features. Or we can say this is the least important. This is not important. The x-axis, this represents the mean absolute shape value for its features. So this is the mean absolute shape value. This is the mean absolute shape value. This is the mean absolute shape value. The absolute part means we look at the magnitude of the impact, not the direction. It means this blue, okay, this is impact to the model. This feature has an impact to the model, and this feature has an impact to the model. And what is the impact? This feature impact to the class 1, this impact to the class 0, and this impact to the class 2. The higher value means the impact is high. The low value, the impact is low. If you see this one, the impact is low because the shape value is lower than this one. The sepal length, I think this is the lowest one because there is nothing here. The bar plot length, the bar length. The longer the bar for a given feature, the greater its average impact or the magnitude of influence on the model's output or the prediction across the entire dataset. So because it is long, then this feature is highly impacting the model. Essentially, a longer bar means that feature on average has a larger role in driving the model's prediction. So if you want to get a good prediction, make sure that you include these features because these features will improve the accuracy. These features will improve the precision, will improve the recall, and of course, it will improve the F1 score. We can also produce this kind of plot. So the plot of the shape value, like this one, it is similar with the regression. We have the dot. Okay. So this is dot. Dot. Every of this one, there's a dot. 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 So each dot represents an observation. every single dot on the plot correspond to a Shapley value for a specific feature for a particular data instance. So one row in your X test data. So if we have the X test data equals to 30, then each dot, it means one data in your testing. This is another data in your testing. This is another data in your testing. And we can see the spread and the density. The spread, the density means the horizontal spread of the dots for a given feature show the range and its impact. Okay. So this is the horizontal. If you look at these figures, okay, profusely, you can see this is the absolute value. What is the absolute? Absolute means we turn the negative value into positive. Okay. So this one, you can see some of them are in the negative and some of them are in the positive. Using the dot, you can have the negative and positive. But using the bar plot, previously, we put everything, this negative, into the positive. So we can see the magnitude. The horizontal spread, in this case, you can see the impact of these features. In this case, some of the data are in the most left and some of the data are on the most right. The density of dots indicates how many instances have similar shape value for that features. Then you can see there are many testing data that has similar shape values. There are many data have similar shape values here. The y-axis, again, it is the same with the bar plot. It shows the feature importance order. The order here means the top is the petal length, next is petal width, the next is sepal width, and the last one is sepal length. The features are listed on the y-axis, typically ordered by their global importance. Okay. Features at the top are generally more impactful. And the order is usually determined by the mean absolute shape value. Okay. So we look at the bar plot. Based on the bar plot, we can see how big is the shape value. The x-axis, it means the shape value. It is the impact on the model output. So the x-axis here, we have the positive and negative. It shows the Shapley value for each feature. A positive Shapley value means the feature value pushes the prediction higher toward predicting the class 1 if it is binary classification, or towards the higher score for the predicted class in multiclass. Can you understand? If it is binary classification, what is it? In binary classification, we have 0 and 1. So if it is a binary classification, we can easily say that if it is more on the left, yeah, it is toward plus 0. If it is more on the right, it is more on the class 1. However, if we have multi-class means more than 2 classes, more than 2 values on the label. Then it means we need to see towards a higher score for the predicted class on the multi-class. So there will be some score. If you look at the decision tree, among 80 samples, we have, for example, 0, 41, and 39. Then it means we know that this is the higher score from the prediction. Then we call this is more toward predicting the Virginica because this is the higher score. In this case, yeah, we are not sure what is the class because it is a multi-class. A negative shape values, it means the feature value puts the prediction lower, away from class 1. It means the magnitude of the shape value indicates the strength of the impact. So this value, it is away from the class. Maybe if it is the petal length, the small petal length, it is more to the setosa. If it is high petal length, it is more either on the virginica or versicolor. The color itself, it represents the color of each dot represent the original value of that feature for that particular instance. So red indicates high feature values and blue indicates low feature values. So blue indicates low feature value and red it indicates the high feature values. Okay, so let's look at the code. You can use the plot tree. So this is the text from the plot, and you can get this decision tree. Okay. So we already learned how to understand this decision tree. And for the shape, you can install the shape library. Because we are using the decision tree as the analysis for the analysis, so I call the decision tree classifier. I call the model decision tree classifier to get the explainer. And then I explain this one based on the data on the testing set. So we want to see the global feature importance using the bar plot. So I'm using the bar plot, which is the plot type is bar. And the feature names, I'm using all the data and I'm just looking at the columns. So we can get this result using the bar plot. So this value is positive because we want to look on the impact of these features and we do the absolute. If it is negative, then it becomes positive. And we can do with the explanation in the dot. So this is the dot plot. Using the dot plot, we can get the negative and positive. So some of the testing data are in the negative or it is pushing away from the prediction result, and some of the data are positive, so it is more impact on the prediction on particular class. Petal width, there are some impact, but the sepal width and sepal length is not that important in this case. Okay, I think that's all. So we learn about the classification. We learn about the KNN. We learn about the performance improvement using the holdout, the cross-validation. And we also learn the model comparison and how to interpret the model and using the shape values. Okay, any questions? If